Welcome to this explainer, where we're basically going to decode the fundamental language of computing. Okay, let's just dive right into this by breaking down the highly organized logical classification system of the 8085 microprocessor. If you've ever wondered how mere silicon is organized to actually think and process information, well, you are absolutely in the right place. We're going to look at the exact taxonomy that makes this foundational tech tick. Here is our quick roadmap for today. We'll cover the microprocessor's vocabulary, classification by function, how chips actually find data, sizing up those instructions, and finally, putting it all into action.
All right, let's kick things off with Section 1, the microprocessor's vocabulary. So when we talk about getting a chip to compute, we first have to understand the sheer scale of the language it speaks, right? It needs a basic vocabulary to understand what we want it to do. And here is the magic number, 246. The 8085 microprocessor supports exactly 246 unique instructions. Now, at first glance, trying to memorize or utilize nearly 250 different commands sounds completely overwhelming. But as you'll see, you don't have to just memorize a random list. They are perfectly and logically classified.
To really understand that classification, we need to quickly define our terms. An instruction set is the entire group of these 246 instructions. You can basically think of it as the microprocessor's complete dictionary. Inside that dictionary, each specific instruction is represented by an 8-bit binary value. We call this 8-bit binary value the opcode, or instruction byte. It's the specific binary word the microprocessor reads to know exactly what task to perform next. Moving right along to Section 2, classification by function.
To bring some order to the chaos, we categorize those 246 opcodes into distinct functional groups. If the instruction set is a dictionary, these groups are kind of like the verbs of human language. Every single command falls neatly into one of these fundamental buckets. We've got data transfer for moving information around. We have arithmetic and logical groups for math and Boolean operations. The branch group handles jumping to different parts of a program. And then we have the stack I/O for input and output, and machine control for things like halting the system or enabling interrupts. It really is a beautifully organized taxonomy.
Let's zoom in on one of these for a second. The arithmetic group acts as the absolute heavy lifters of our silicon vocabulary. This is where we find commands like add to add to the accumulator, sub to subtract, and INR or DCR to increment and decrement bytes by 1. Basically, whenever your computer is crunching numbers, it's leaning heavily on this specific functional group.
Then we have the branch group. I like to call these the decision makers. This group is fascinating because it allows the microprocessor to change the flow of a program conditionally. Instead of just mindlessly reading line after line, commands like jump, call, or return can be triggered based on specific conditions, like whether a previous calculation resulted in a 0 or a carry. This is where basic logic routing actually happens. Okay, let's jump into Section 3, how chips find data.
So we've moved past the verbs, the functions, and now we really need to look at the subjects using addressing modes. Because think about it, a command is totally useless if the chip doesn't know where to find the data it's supposed to manipulate. Addressing modes are simply the different pathways a microprocessor uses to access data. This is a critical secondary layer in the logical classification of our instruction set. Just as we sort by function, we also sort by how the data is actually addressed. Let's contrast a couple of these modes. On the left, immediate addressing is when the 8 or 16-bit data is literally part of the instruction itself. Commands with an I in them, like MVI, often fall right here. You're handing the data directly to the chip. Now on the right, register addressing transfers data directly between the microprocessor's internal registers. This is much faster because it completely skips accessing the main memory locations entirely.
And this brilliantly illustrates two more modes. Indirect addressing is kind of like giving the microprocessor a treasure map. The actual memory address where the operand is located is specified by the contents of a register pair. Contrast that with implied addressing over on the right. Here, the command is so incredibly simple that the opcode itself implies the target. For example, CMA simply complements the accumulator. The address is just baked right into the command itself. Which brings us to Section 4, sizing up the instructions. You see, our taxonomy is multidimensional. Beyond function and addressing, we have a third major classification system: sentence length, or byte size. The 8085 classifies everything into 1, 2, or 3 byte instructions based purely on how much memory is required to store them. A simple command like moving data from register B to the accumulator takes just one single byte, the hex code 78H. But if you want to load a specific immediate piece of data, like 05H into register C, well, that requires 2 bytes, one for the command, one for the data. And to load a full 16-bit address, You're going to need 3 bytes for that.
Let's actually see how a 3-byte instruction builds its logic. Take the instruction LXI-H, 9000H. The microprocessor first reads the 1-byte hex code 21H, so it knows the command is to load the HL register pair. But it needs the address, which is 9000H. So it takes up 2 more entire bytes of memory, 00H and 90H, to store that specific address. So that's 1 byte for the action and 2 bytes for the massive address target.
All right, the final stretch. Section 5, putting instructions into action. We've seen the taxonomy, right? The vocabulary, functions, addressing, and sizing. Now let's prove why this logical classification actually matters. Here is a genuine assembly program designed to subtract 2 8-bit numbers. Notice how beautifully the classifications we just learned work together here. We use a 3-byte data transfer instruction, LXI, to point to our memory location at 6000H. We use single-byte arithmetic instructions like INX to increment our pointers and sub-m to actually perform the subtraction. Finally, we use a machine control instruction, HLT, to terminate the execution. And just like that, the result is safely stored at memory location 6002H.
But here is a massive plot twist for you. For all its structural elegance, the 8085 microprocessor literally has no native, direct instructions for multiplication or division. Crazy, right? Despite having 246 precisely classified commands, this foundational piece of technology never actually learned how to directly multiply. So, how do we multiply? Programmers cleverly use the functional groups together as a brilliant workaround. They rely on successive addition. To multiply, you clear the accumulator and then use the arithmetic group to add a number to itself, while using the branch group, specifically a command like jump on not 0 or JNZ, to loop that addition over and over until a register counts down to 0. You essentially build multiplication entirely out of simple adding and conditional jumping.
It's truly a marvel of structured logic. Which leaves us with this final thought for the day. If an 8085 can perform incredibly complex programmatic tasks, using nothing but a perfectly classified dictionary of 246 simple 8-bit instructions, what kind of logic is powering the screen you're looking at right now? The taxonomy we explored today isn't just ancient history. It is the fundamental structural blueprint of literally all modern computing. Thanks for joining me on this explainer, and definitely keep questioning the tech around you.